The complex plane. The complex plane looks quite a bit like our typical coordinate plane. The biggest difference is instead of x and y, we're going to have a real component and an imaginary component, just like all imaginary numbers. So the x-axis is now the real axis, and the y-axis is now the imaginary axis. So that means if I'm going to plot a point like 3 plus I, which is 3 plus 1I, I'm going to be plotting the point 3, 1. So 3, 1 represents the point, or represents the complex number 3 plus I. Whereas negative 2 minus I would be the point negative 2, negative 1. So negative 2, negative 1 would be that point on the complex plane. The absolute value or modulus of a complex number z equals a plus bi is simply the distance between the origin and that point. So what we're going to do is going to feel a lot like when we had some vector in component form and we wanted to find its magnitude, because that was just the distance between that point and the origin 0, 0. And just because the second point is 0, 0, I don't need to take a minus 0 squared plus b minus 0 squared. So we just can take the 0, 0 out of it. We're just squaring the a, squaring the b, and then taking the square root of the sum. So we're going to take a look at z1 and z2. So we're going to plot them on the complex plane first and then find their absolute values. So z1 would be negative 3 plus 2i. Again, that's going to look like negative 3, 2. So negative 3, 2 would be z1. And z2 would be negative 4i. So that's 0 right or left and negative 4 on the imaginary axis. So that's z2. Now we want to find their absolute values. And again, we're thinking if this were a vector, what would be that magnitude? Now this is not a vector, this is a complex number, but that's essentially the same thing. We're just finding the distance from this point 0, 0 to z1 and z2. So for z1, we're going to take negative 3 squared plus 2 squared, which gives us 9 plus 4, or radical 13. So again, that's the distance between 0, 0 and z1. And for z2, we're going to take negative 4 squared and then take the square root, which is obviously going to give us 4. And that makes perfect sense, is that that would be a distance of 4. Also, as we did with component form of vectors, we can think about a complex number as a component form of a vector. So for z1 and z2, if I want to add or subtract them, I'm going to be looking at z1 as 2, negative 3 vector. So again, that's like z1 as a vector. And then z2 would be negative 3, 1. So negative 3, 1, that would be z2 as a vector. And we're familiar with addition and subtraction with vectors, so that's what we're going to do. We can use that parallelogram rule to say if I'm taking z1 plus z2, then I'm going to simply take z2, and it's almost like taking that initial point and shifting it down here. So it's going to look something like this. So adding them together, I'm going to get 2, let me get rid of my little markings. I'm going to have 2, negative 3 plus negative 3, 1 gives me negative 1, negative 2. I'm going to put that back into a complex number. But again, that's that point right here, negative 1 minus 2i, or negative 1, negative 2. Same thing for z1 minus z2. So now I'm thinking about z1, which we know is right down here. But z2, I want to think about the negative version of z2. So instead of negative 3, 1, I'm thinking of positive 3, negative 1. So when I'm doing the parallelogram rule, that's using this version, or negative z2. So now if I do that math, I can take 2, negative 3 minus negative 3, 1 to get 5, negative 4, or 5 minus 4i. We're going to end with distance and midpoint in the complex plane. And yes, I would just like to point out this is a nice short video after section 6.3, which was such a doozy. The distance and midpoint for the complex plane can be calculated in the same way we do in the normal coordinate plane. So even though I'm using x1, x2, y1, y2, and with a complex number, it's typically a plus bi and c plus di, we get that we could just call this a minus c and b minus d, and this would be a plus c and b plus d. Same exact concept. So let's go ahead and find the distance between and midpoint of z1 and z2. Remember, z1 would be 2 comma negative 3, and z2 would be negative 3 comma 1. So distance would be 2 minus negative 3, which would be 2 plus 3 squared, which is 25. And then for the y's, we have negative 3 minus 1, which is negative 4. Negative 4 squared is 16. Add them together to get 41. And of course, take the square root, and that is the distance. So the distance is radical 41. The midpoint would be taking 2 plus negative 3, which is negative 1, divide it in half, so negative 1/2. And then negative 3 plus 1, which is negative 2, divided in half, is negative 1. So if I graph that, this is the point, negative 1/2 comma negative 1. That's the midpoint between those two complex numbers. And the white line represents the distance, which has a length of radical 41. Coming up next, we will finish chapter 6 with 6.6 trigonometric form of a complex number.